So today we're going to talk about the transformation of functions. Typically we're going to be transforming parent functions that we talked about yesterday. And a transformation refers to any type of translating, which means moving, for instance, to the left or to the right, possibly up and down, taking and stretching something. In other words, if we have something like this, we blow it up, or decreasing the size by compressing, we shrink it down, right? Or by taking and reflecting over certain lines or points. So let's get started. We did some of this in Algebra 2. In general, any function can be rewritten in the following form. And the function I'm talking about is any function f of x. So you'll see that in addition to f of x, I have this a multiplied by the quantity of f of x minus h over b plus k. And let's talk about what each of these variables mean. H corresponds to a translation of the horizontal type, left and right. K corresponds to a translation of the vertical type, up and down. A is what I call a y multiplier. The book refers to it as a vertical stretch. And it turns out if your absolute value of A is greater than 1, the graph is going to get narrower or compress. If the absolute value of A is less than 1, the graph's going to actually get wider or stretch out horizontally. If we take and pop a negative in front of that A, it's going to reflect over the x-axis because it multiplies the y by a negative. And likewise, if I have a b value that is greater than or equal or greater than 1, it's going to make the graph wider, stretches it out because I'm multiplying the x value by a number greater than 1. If I have a b value less than 1, then it's going to narrow or compress the graph again because I'm taking some x value and multiplying it by a fraction. And if I multiply an x value by a negative, that's going to reflect over the y-axis. So let's go through and graph a couple of functions, again without a calculator, using these concepts. So in this case, I'm going to identify what the 1 and the 3 have to do with the graph. Well, my parent function in this case is the square root of x. I know the square root of x has a pattern that we generated yesterday of 0, 1, 4. We can throw a 9 in there as well. And I would normally get out a 0, 1, 2, and 3 for my x's and y's. Now what I like to do is I like to identify these two values here. The 1 in this case is an h value, and the 3 in this case is a k value. So what this does is it multiplies, or I'm sorry, what this does is it translates your graph to the right 1 unit and up in this case 3 units. So what I'm going to do is I'm going to graph every one of these points moved over 1 and 3. I like to take and first of all translate my origin, which is 0, 0, over 1 and up 3. So what I really have is I have a new origin point translated to this coordinate here. So what I've done is I've drawn a reference for my translated origin. Now, my graph is going to look the same as it would in the case of its parent function, y equals root x, because there's been no increasing in shape, decreasing in shape. It's just the same exact shape has been moved to the right and up. So really, my graph is going to follow this same pattern as the parent function. So what I should be able to do is graph 0, 0 from my new origin, graph 1, 1 from my new origin over 1 and up 1, graph 4, 2 from my new origin, and graph 9, 3 from my new origin, and then connect these dots and say, well, hey, this is my new curve. Let's say you're not satisfied with that. Let's say you want me to prove that. So what I'm going to do is I'm going to pick any point on this graph. This is the point 2 over and 1, 2, 3, 4 up. So this point 2, 4 should be a solution to this equation. Well, let's plug it in. Find out. I've got the square root of 2 minus 1 plus 3. It better be 4. So I get the square root of 1 plus 3, which is equal to 4, and it checks. So I've graphed this right. Now I prefer to use this method rather than just plugging and chugging general points. You can kind of do what you want to do, but I think this is going to be most effective in the long run, especially as I get more transformations within the problem itself. It's going to require a lot less work too. So let's move to another example. This is very similar. We have a parent function of a cubed. I have a couple of translations. Now rewriting this in its standard form, I have x minus h. Well, if I want to make this a minus here, I need to have minus a negative 4. Therefore, that means that my h value is equal to negative 4 and my k value is equal to a negative 1, which means I'm moving to the left and down for my translation points. Notice there's no a and b involved in the problem, or if there is, a is equal to 1 and b is equal to 1 as well, which means there's no stretching or compressing. The function's going to look the same as x cubed and have the same pattern. You know the pattern for x cubed is going to be negative 2, negative 1, 0, 1, 2. You get negative 8, negative 1, 0, 1, 8. So from my new origin, which is 4 to the left and 1 down, I'm just going to put a fictional set of axes here. I graph this pattern. So I'm going to go over 1 and up 1, over 2 and up 8, go over 1 and down 1, go over 2 and down 8 from that new origin point, and graph the function. Again, just to check ourselves to make sure we did this right, pick a sample point, and I pick any other sample point other than the new origin. So I'm going to go, let's just go over here, 1, 2, 3, 4, 5, negative 5, negative 2. And make sure that point satisfies the original equation. So if I go y equals negative 5 plus 4, I cube that and subtract 1, I better get negative 2. You'll notice I have negative 1 cubed minus 1, which ends up being negative 2. Satisfies my equation, thus I graphed it correctly. So now we're going to start stretching, compressing the graphs, because you'll notice in this case I have an a value of negative 3. My h value is equal to 2. Therefore, I'm going to take with this 2 and I'm going to move to the right. With the a of negative 3, this is a y multiplier, and I'll show you how this fits into the whole scheme of things in a second. My parent function is x squared. It has a normal pattern of negative 2, negative 1, 0, 1, and 2. So this goes to 4, 1, 0, 1, 4. Here's my x. Here's my y. And in this case, what I have is I have a y multiplier. So I'm going to take and multiply all my y values by a negative 3. Thus, I get negative 12 here, negative 3 here, 0, negative 3, negative 12. And this problem has told me I'm going to take and translate all my coordinates 2 to the right. So my fictional origin is now at 2, 0. And from 2, 0, I've changed my actual pattern. My actual pattern, instead of going over 1, up 1, over 2, up 4, is now I'm going over 1, down 3, and over 2, down 12. So from this new origin, I go over 1 and down 3 on both sides, and go over 2 and down 3, 6, 9, 12. Get a graph that's a stretched out parabola. Right? And once again, I'm going to check a point. So this is the point 1, 2, 3, down 3. And that needs to satisfy my original equation. So my original equation states I have negative 3 times 3 minus 2 squared is equal to y. And that better equal negative 3. So this is negative 3 times 1, which is negative 3. Satisfies the equation, so I've graphed it correctly. Once again, we have a parent function of x cubed. I have an a value this time of a half, which is in absolute value less than 1, so this should be actually compressing my y's or making it smaller in size. And I have an h value of 2 and a k value of negative 1. K value of negative 1 translates down, h value of 2 translates to the right, and an a value of a half is a y multiplier. So I'm going to look at my basic pattern once again for x cubed. I get 2, 1, 0, negative 1, negative 2, and I get 8, 1, 0, negative 1, negative 8. Here's my x, here's my y. But in this case, I'm multiplying all my y values by a half. If I multiply 8 by a half, I get 4. 1 by a half, I get a half. 0, 0, negative 1, negative 1 half, negative 8, negative 4. So I translate over 2 and down 1 for my new fictional origin, if you will. And from that new origin point, I'm going to graph the following pattern of x and my transformed y value. So I'm going to go over 2 and up 4, over 1 and up a half, back 1 and down a half, and over 2 and down 1, 2, 3, 4. All from that new origin translation. And then I'm going to take and graph my function. Again, I'll check a point. Here's 0 and 1, 2, 3, 4, 5 of the negative type. And I'm going to plug that in and make sure it works. So I have y equals a half times 0 minus 2, quantity cubed minus 1. Better be negative 5, so I have a half times negative 2 cubed minus 1. This is a half times negative 8 minus 1, which is negative 4 minus 1, or negative 5, and it checks. So once again, there's the graph of that. function with transformations. This next problem, we introduced a b value. You'll notice in this case that I have a b value of 3, since v is in the denominator in this case. I have an h value of -4 and a k value of 2, which means translates up 2 to the left 4, and I have now an x multiplier of 3. My parent function in this case is root x, so x and y, 0, 1, 4, 0, 1, 2. But in this case, I'm going to multiply all my x values by a factor of 3. So when I multiply 0 by 3, I get 0, 1 by 3, I get 3, and 4 by 3, and I get 12. So now, rather than this original xy being my pattern, I have this new pattern of over 3, up 1, over 12, up 2, from my new translated origin. And my new translated origin is over 4 and up 2. Which puts this fictional origin here, and from that point I'm going to move over 3, up 1, over 12, and up 2, and graph that new function from there. So let's pick a point. This is the easier one, probably -1 and 3, and make sure that conforms to our original equation. We have y equaling square root of -1 plus 4 over 3 plus 2. This gives me 3 over 3 in the radical plus 2, which is 1 plus 2 or 3. So the point -1, 3 conforms to the original function. Thus, I've most likely graphed it correctly. Everything we've been given up to this point has been in standard form. This function is not. Remember, our standard form is a x minus h over b plus k. Well, in this case, I have a 2 multiplied by an x, and in the standard form, we have a coefficient of 1. So what I need to do is make sure I have a coefficient of 1 first. So in order to get a coefficient of 1 for my x value, I have to factor a 2 out. And then we notice in our original we had an a times the function itself. Well, this is an x squared function. And this 2 is actually inside the function. So if there's something inside the function as opposed to outside the function, whatever's inside the function must be a b value. Now the b values in this case have to be in the denominator. So to have a multiplication of 2 represented by a division, I have to take the quantity of x minus 5 and divide that by a half. You'll notice that anything divided by a fraction, I multiply by the reciprocal, so this is the same as multiplying by 2. So in this case, I have a b value of a half, an h value of 5, and a k value of -7. -7 means I move down, 5 means I move right, and I have an x multiplier of a half. I'm going to translate over 1, 2, 3, 4, 5 down 7. Like so. we'll look at our pattern, which is an x squared pattern. So in this case, if I start with an x and a y and I have 2, 1, 0, 1, negative type, negative 2, I have 4, 1, 0, negative 1, negative 4. And in this case, I'm multiplying all my x coordinates by a half. So 2 times a half gives me 1. 1 times a half is a half. 0 is 0. Negative 1 half. And negative 1. So from this new origin, I'm going to move over 1 and go up 2 in both directions. And then I'm going to go over a half and up 1. So you'll see this parabola is kind of compressed vertically. And I'm going to take one of those values again. We'll take this point right here, which is 1, 2, 3, 4 over, and 1, 2, 3, 4, 5 down. And make sure that conforms to the original equation. Therefore, I have y is equal to quantity of 2 times 4 minus 10 squared minus 7. Hopefully I get negative 5 out. So this is 8 minus 10 quantity squared minus 7. 8 minus 10 is negative 2 squared is 4. Looks like I'm going to have a little bit of a problem here. I might have calculated something wrong. And I get negative 7. So let's check to make sure I've done this right. This ends up being negative 3, which is a problem because I want a negative 5. So let's make sure I've done all this correctly. Alright. I went over 0 and up 0. I went over a half and up 1. And I went over 1 and up 2. But you'll notice this asked me to do over 1 and up 4. So basically I just followed my chart incorrectly. So let's go and correct that. All part of the plan because I wanted to show you one where I just wasn't paying attention and had to go back and check my actual chart to make sure I graphed this correctly. So let's go back, go over 5, down 7, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. Here is my new set of origin. And now I'll go over 1 and up 1, 2, 3, 4, over a half, and up 1. And you'll notice there's our graph. It's been squeezed in. And this new point of 4, negative 3 exists on my graph and checks by the equation I just worked out. So this is a good instance where you really do want to check one of the points on your graph to make sure it turns out correctly and you've done all the processes correct. Okay, we're going to shift from graphing now to writing equations based on the transformation we want. I have a parent function of x cubed, and I want to shift this to the right, so that's a translation. So 6 must represent my h value. If I want to stretch something vertically by a factor of 2, vertically corresponds to y's. And I want a y multiplier of 2, which means that's got to be my a value. So let's go ahead and rewrite this. Y equals a, which is 2, times f of x minus h. So that's x minus 6 quantity cubed because that's f of x. There's no k translation, so I don't have to worry about that. And there's no x multiplier, so I don't have to worry about that. So my equation can be written as 2 times x minus 6 raised to the third power. Lastly, we're going to take and say that I've got some point on a graph, and I want to know where that point is going to be moved, assuming that I have 4 times f of x. Well, if we think about this, 4 is equal to my a value. And what does a actually do? A is a y multiplier. So what that says is it says all my x movements are going to be the same, but my y translations or my y movements are going to be multiplied by 4. So assuming that I have originally gone over 5 and up 3 and plotted a point there, my horizontal movement's not going to change. It's my vertical movement that will be multiplied by a factor of 4. So instead of going over 3, I'm going to go up a factor of 4 times that. 4 times 3 is just 12. So really, I'm going to be moving up 4 times that value of 3 to 12. So my new point will be at 5 and 12. All right. That's it for the day. Take and fill out your lesson summary. Hopefully a lot of this was review, and go to my math lab, do the assigned problems.